Scenario. An amusement park ride has identical carriages that revolve around the center of the ride's axle, as shown in the figure. Both carts travel at a constant tangential speed at all points along the circular path with a radius r. Two friends that weigh the same are on separate carriages. Friend A is on carriage 1 and friend B is on carriage 3. As friend A carriage passes through the top part of the ride, he feels the seat exerts a normal force with a magnitude of zero point 0.6 force of gravity. Question. Describes the passenger's linear velocity while passing through the location where carriage 1 is at. Answer. The linear velocity changes because the direction of the vector changes. This is the carriage before it reaches the first location, and when it reaches the first location, that's the new linear velocity. Notice that the direction of the vector changes, therefore the linear velocity changes. Next question. Describe the passenger's angular velocity while passing through that location where carriage 1 is at. Answer. The angular velocity is actually constant, and the reason why is because the change in the angular theta does not change. Delta theta, which is the change in the circumference around the circle, is equal to 0. Angular velocity is equal to delta theta over delta t. So here you would say that the angular velocity is constant. That gives you a visualization of the angular velocity in this scenario. If the ride was designed better, such that the radius increased, how would that affect the passenger's linear velocity and angular velocity? In short, it's asking how does radius affect the linear velocity and how does radius affect the angular velocity? Here's the answer. Well, v is equal to r omega, which is velocity is equal to the radius times the angular velocity. So here you should notice that the linear velocity will increase when the radius increased. V goes up if r goes up on the right hand side. Likewise, the increase in the radius will not affect the angular velocity because there is no r in the delta theta equation for the angular velocity.